Euler-Lambert law is represented as A equals epsilon LC, or log base 10 I over I initial equals epsilon LC. On the left side of the equation, the A variable represents absorbance. The way to find this can be log base 10 times I over I initial. I initial represents the intensity of the light passing through the reference cell, while I represents the intensity of light passing through the sample cell. On the right side of the equation, there is the Greek letter epsilon. There is also L representing the length of solution the light passes through. You can find this by measuring how wide the cuvette is. Lastly, the C variable represents the concentration of the solution. You might know this at the beginning, but if you do not, you can go through the equation and solve for this unknown variable. The spectrophotometer will tell you the absorbance value. There is a direct relationship between absorbance and concentration, meaning that when the concentration increases, the absorbance will also increase. You should also zero the machine with a blank before you go through your solutions in order to have a control to compare your other values to. If you don't do this, your data might be skewed because of environmental changes like temperature or previous groups measuring their solutions.
Remove the blank solution and begin testing your other samples. Make sure to record the wavelength and absorbance for each sample.
My name is Brooke Carr, and I'm going to be providing you with 2 examples of why you would scan across all wavelengths on the spectrophotometer. I'm also going to be explaining how scanning across all wavelengths can help you find the lambda max and what the lambda max is. One example for why you would scan across all wavelengths is to find the most useful wavelengths for measuring the absorbance of a solution, just like we did in this experiment. Another example for why you would scan across all wavelengths is to find the peak where a spectral shift has occurred, such as a change in solvent polarity. This peak would be called the lambda max, which is the point where the absorbance is maximum.
After recording the wavelength and absorbance, we can use those to find the concentration of our unknown. We then use M1 V1 equals M2 V2 to find the concentration of the stock solution, first dilution, and second dilution. Now we use 2 points from the data we found and plug it into y2 minus y1 over x2 minus x1. This gives us the slope. Finally, we plug in the absorbance of our unknown for y equals our slope times x plus b. In this case, b equals 0, and we found our slope to be 7,000. Solving for x, we get 2 times 10 to the negative 5th. Remember to dispose of everything accordingly, clean your lab station, and wash all the instruments.